Hey, John here. Let's take a look at this stretching synchronizer that I've been tinkering around with. This is more useful in certain situations where you are sampling an input at a frequency that's not significantly greater than the widths of the signals that you're trying to detect. As always, a big thanks to everybody supporting the channel. I always appreciate it when people like the videos and subscribe to the channel, especially those that are Patreons, especially the VIPs listed here that have gone that extra mile. Thank you very much. I've already talked about the cross-domain problem, the clock synchronization and all that, at an introductory level, and we kind of kicked under the rug a few of the details of what's going on there in order to just simply say, hey, this can work for you. All right, but it only works for a certain type of problem, and by that I mean in the sample code. Let's go up and have a look-see for a real quick recap, so that if you're just joining now, you can go look for the playlist that this video is part of, see the description and below the video on YouTube, and you can see what that's all about. Now, I talked about this before, so a quick recap, and hey, here's a link to the video and stuff on that, and where you can get the your own copy of the source code, the example files, and all that. See the links below the video on YouTube. And this paper right here is where some of the stuff I'm talking about is discussed in more detail as well, if you want a written form of this stuff. Okay, and this Sunburst design and this Burton Cummings, he's the singer for the Who, the Guess Who, from Canada. Cummings is the name of the guy that wrote these papers. That I think he works at Sunburst Design or something like that. He's got a whole bunch of papers, really good discussions on topics like metastability and synchronization. And this paper right here is one of the things that I use for source information on my videos. This particular piece of code is what I talked about in the past. And what this is doing is it creates a shift register with from 0 up to 2 minus 1, 0, 1 is a 2-bit shift register. All right, and the way this thing works is every time my this is the what we call the destination clock domain, right? The logic that's receiving a signal. In this case, I use it to receive a signal that was from an external source from an FPGA coming into the FPGA. Every time the FPGA clock would tick, and a single clock running at what I would argue would be a very high frequency relative to the how often the input signal would change its value. Okay, and that's key for this sort of thing. You need to understand what is the relationship between the shortest period of time that this input signal will remain high and or remain low. Not the period of a free running clock or anything like that. You need to know, does this clock tick a couple of times? At least 1.5 is kind of a magic, rule of thumb here. As long as this clock will tick 1.5 times more often than this thing here will ever change, you're relatively okay. Okay, so that basically would mean that your sample clock would always have, in this case, one positive edge, maybe two, that it would occur while this signal is in a constant state, either high or low, so that you'll always be able to sample it with a clean setup and hold time. And today what I want to talk about is what happens when you don't have that guarantee. When this clock frequency here is not at least 1.5 to 1 faster than whatever the clock domain is, and theoretically that would be used to generate this signal over here, or this free running, external signal, even if it's a push button or something like that. You have to sample it more often than the frequency that is behind its own changing. I mean, that makes sense, right? If you don't look periodically at this input signal and the input signal changes and then it flips back to what it was before and you weren't looking, then you would miss it. It's as simple as that. So you have to sample it with a clock. The period, the rate of checking the current value on your input has to be greater. You have to check it more often than it is expected itself to ever change. Okay, and this circuit will do that just fine, and it will basically what it does is it shifts this continuously into the shift register. And the idea is that if this input signal changes really close to the same point in time where your sampling clock has its active going edge, in this case it would be the rising edge of the clock because it's positive here. If this clock ticks on a positive edge at the same time the input is changing, that may or may not be ingested in the way you hope that it is, and that is if it changes from a 0 to 1 while your clock is ticking, you might hope to see that it is 1 when it's being shifted into the shift register here. And it may not be if it doesn't meet the setup and or hold time of the flip-flops inside your FPGA. And that's why you want to make sure that this clock is going fast enough that you might see it again a second time when it is in fact that close. All right, so that's what's going on here. So the first bit when it's shifted into our sampling shift register could be garbage. It could go metastable for a little while, which is a huge problem in a high frequency FPGA circuit. Almost all circuits you have to deal with this, but it gets worse as your sample rate increases, because metastability is this, the latch will kind of quiver up and down and up and down. Not sure I want to be a 1 or a 0, and it finally ekes out and settles down after a while. And if the rate at which you sampled this clock is too high, and this is not settled down by the time it samples it its second time, you have a problem. Now, in the designs I've been tinkering with on this channel, we're running it between 25 and 100 megahertz, and that's not considered all that fast. And a 2-bit shift register like this should do the job just fine. It should settle down in that amount of time, such that as it shifts through this shift register, even if it quivers around for a while, it'll probably be settled down by the time the clock ticks its second time and the thing shifts to the right into this shift register, right? That's the whole ball game here. But what happens when your sample rate is not faster than the rate of change that you're really monitoring, okay? So what we're going to do is what are you going to do? I'm going to stretch out any pulse that's arriving into my circuit. That's the solution. Oh, I only check once every second. But what if it goes on and off, and it's only on for a quarter of a second? I might miss that. All right, well, how can we solve that? There's many ways to solve it. One way to do it is to just stretch out any pulse to a really long pulse from the thing generating the pulse that's too short. Basically, if you can't handle a pulse that's only a quarter of a second, tell whatever is giving you that quarter of a second pulse to give you a longer one. That's what we're going to do here, okay? Make it long. Oh, it doesn't hurt. Doctor, it hurts when I move my arm like this. Doctor tells me, don't move it like that, right? The old joke. So what are we going to do? I'm going to build a thing that stretches out pulses. So we have 2 clock domains. That's the number one requirement for crossing a clock domain, is you have 2 clock domains. Now this is specifically designed as an example. I'm going to present it standalone, but I'm using it for a project that I've been working on. And in this project, what I have is a situation and such that I have literally a free running clock. 2 of them, in fact. I have a source clock domain and a target clock domain, and they're running at different speeds. It turns out in my case that the second clock domain is running a little bit faster than the first one, but it's not running 1.5 times faster, which is, like I said, the rule of thumb. As long as you're 1.5 times faster than in the target clock domain, then the clock would change. It would tick a couple of times. It would give you 2 chances to see something that's running at the slower rate here, okay? But I'm not going that fast, so at best we might only have 1 chance to see it. And even then, if it happens too close in time to when this clock has its active going edge, I might miss it due to metastability, okay? So what we're going to do is we're going to say, here's this clock domain number 1, and this input signal is generated in this clock domain. Therefore, this signal is known to be synchronous in the clock domain number 1. And I put that up here. It's assumed that in is a clean 1 clock, 1 period long tick signal. And I use this word the way some, at least one author I've read uses it. His name is Pong Shu, and if you Google it, he writes some books on how to program VHDL and Verilog and stuff like that. And he refers to these things called a tick signal, which is a tick. It's a signal that goes high on the active going edge of a clock and stays high, or it stays active, okay, until the following active going edge of this clock. So it's literally 1 clock period long in some clock domain. So, and we'll see that in a waveform diagram I'll open up in a little while. So in other words, this in this design expects in to be a 1 period long signal that goes high in this particular case and then goes back low on 2 consecutive rising edges of clock 1. And what this circuit's going to do is it's going to change it over to a signal that goes high for more than 1 period in clock domain 1. It's going to stretch it out. How is it going to do that? It's going to use a counter, which is right here, and this counter has this many bits in it. It's configurable. I'm going to say it has 1 bit in the smallest configuration. So it's going to count to 1. It'll count twice. What this is going to do is it's going to double the length of this signal. So if you think about it, if clock 1 and clock 2 are about the same frequency, but they may be a little off or out of phase or something like that, you have to deal with this clock domain crossing issue. So if that's the case, and I take this 1 clock 1 period long signal, and I use a circuit to change it into a 2 period long signal, then I know it's going to be high long enough to be seen by this guy here. All right, and in the README file that we're just looking at and other notes that you might find, the real issue with synchronizers is that I can't give you one that just says this is good for anything and your problem goes away. That's not how this works. It's annoying, and I hate it every time I got to do one of these. I got to think about it. Sometimes it's fun. It's a challenge. Other times it's like, I got to do this again. And the reality is you have to really think about the situation that has been presented to you and then decide how you're going to address it, because every time it's different. No pun intended, okay? So what do we got here? We got a mixed bag of 2 things going on. We have this pulse stretcher, which is this guy right here. And okay, so what it is it's your sequential and your combinational circuit pair in here. I've talked about this before. It's a really simple finite state machine that just counts from 0 to 1 and then back to 0 again. That's this code here, all right? So a bird's eye view. Let's look at the rest of the code in here. This down here, whoa, is another one of these things where we have, this is going to be the synchronous part of the circuit, and it's so simple that all I'm ever really doing is shifting down here. This is a synchronizer that you just saw in the other project, so I just pasted it in here basically. But this one has to be, doesn't really have to be, I played around with this a little bit. Well, we'll see down here I have a little different situation in how I generate my output signal. I don't simply take, as you saw a minute ago on the screen, this FIFO 0 bit was assigned to the output in the prior example. So this is not the same thing as just simply taking this code up here and then gluing it on to the generic synchronizer I just showed you, because the generic one is designed to deal with a clock. In this example, it's this clock domain number 2 running significantly faster than the clock domain that's generating the other signal, all right? So this is going to work a little bit differently down here. Again, this will make more sense with the test case, but a bird's eye view, we have to specify the length of the synchronizer that's in the clock domain 2, and we want to specify how many bits are going to be in our counter that we stretch out our signal in clock domain 1. And I can see this comment probably could be better. This is how many clock 1 periods to stretch to, and then this is going to be the number of bits in the clock 2 domain. All right. So what are we doing here? We're just counting. That's all we're doing. This just simply this is the usual thing. You got a state machine on reset, set the counter to 0. If it's not in reset, then just take the next value that comes from the combinational circuit down here. And this simply says what? Unless I say otherwise, the counter does not advance. We set in wide to 0, and we'll see that in wide is, where is it defined? It's up here somewhere, right there. This is going to become the output signal, or represent, not rather, it's the output signal of the stretcher. Okay, not of the whole synchronizer. This is the thing that's going to become 2 clocks wide, and it's going to become 2 clocks wide because it's going to be 2 to this power in this case. If I set this to a 2, then it would be 4 clocks wide, and so on. Now this one I just designed to use powers of 2 for how much we're going to magnify the width of this signal here. You could change this and set it to whatever you want. Again, you know, that best suits your needs. This is good enough for mine, and it's real simple. So let's do this, right? So by default, I'm going to set the wide input to 0 unless otherwise down here. So what I'm going to say is if the input is high and my clock counter register, that's an OR. If the input is high, then go ahead and set the wide value. Why? Because it's going to track the input. But remember, the input could go 0 again very soon. But we know that the input in clock domain 1, which is running our circuit here, will be wide enough. It'll be exactly 1 period long of this clock. Okay, so I know that this will stay true until the counter register advances. So what's going to happen here is if the input is true or the counter has already moved on from 0 to 1, I'm going to set the output, the wide version, to 1, and I'll advance the counter. So what will happen is when this goes high, I'll advance the counter to 1 on the next clock tick up here. And during that whole time, this is a combinational output, the output will be set to 1. And it'll stay there until in changes or the counter goes back to 0. Okay? Now, that's not going to happen until the following clock, at which point in will be 0 again, because it will have then gone, you know, its period will have lapsed, and the counter will then go to 1, so it'll stay 1 for a second period of the, you know, clock domain 1, then it will count plus 1, and it'll overflow and go back to 0, and this circuit will then have this be false, and the output, the wide version, the wide output will be 0, and the counter will stay at 0 and stop counting. All right, so that's what this is doing down here. Really super simple state machine implemented with a single if statement like that. Okay, now down here, this is going to use this wide output from there, and it's going to run on the second clock domain. And this mostly is a regular old synchronizer, except notice here, this is synclen plus 1 total bits. Usually you'll see me saying something like, oh, it's the number of bits is like synclen. Might be, I think I said it's a 2 up here, right? Well, quite often you'll say synclen minus 1 colon 0. And that would represent then 2 bits if synclen was 2. But by doing this, synclen is 2 through 0. So that's 2, 1, and 0 for a total of 3 bits. So what this is doing is being 1 bit more than the previous code example. First of all, then why I said, note, by the way, this is synclen plus 1 total bits, because you got to include the 0. Then down here, what happens is, as long as I'm not resetting the circuit, the FIFO gets loaded just like we did before with our input value, followed by whatever remaining bits are in our FIFO. In this case, in the default config, it's going to have 3 bits in it. So it'll grab 2 bits that were, in the FIFO before, throwing away the least significant bit, and it will shift in the new input value in the most significant bit every time clock 2 ticks. So this is a pretty much generic synchronizer. Down here we have a little different situation here. The output of this whole thing we set to true if sync FIFO 1 is high and sync FIFO 0 is low. Again, if you can't follow this in your head, we'll see it in the waveform in a second. What that's doing, if you think about it, if the FIFO is all zeros, like here after it's been reset, and it'll still be 0 as long as clock 2 is ticking away without reset being true, and your input is 0, it just sits there all full of zeros. If in wide from the input up here ever goes to be true, what'll happen is this will start shifting in bits. And by the time clock 2 ticks twice, it will shift in 2 of these into this 3-bit shift register, and we'll have a 110 in there. At that point in time, this expression will be true for one single clock period of clock 2, and out will go true for one period of this clock 2. All right, which is what I want, because I want to take, big step back again. Think about it, right? The in signal here is a 1 period tick signal in the clock 1 domain. And the out signal that we're going to generate in response to seeing this in signal come by is going to be a 1 tick wide signal in the clock 2 domain. Okay? Now that's exactly what I want to do in a project that I'm working on that is, generating a status, a data transfer signal, a pulse that I have to recognize and then ingest in my FPGA. So this is what I want. This is what I decided to try and do here. So I'm going to have a test case. I create the unit under test. I'm not overriding any defaults. I got a reset. I got the 2 clocks and an input and an output. It's a pretty simple test case. I reset it, wait a while, turn off the reset. All the other stuff is initialized to 0. These clocks free run. I got playing around with 2 different frequencies. What happens if clock 1 is going along and clock 2 runs slightly faster or slower than clock 1? What does this circuit do? What are the pros and cons? So here it is running slower. We can start with that one and we can see what happens, and we can take a look at the other one. So what do we got down here? If you look, what I'm doing is I'm generating, every time I wait 2 ticks, that's 1 period of a 50-50 duty cycle clock, in particular clock 1, because clock 1 is free running with 1 time period between each, if it's 180 degrees of phase. So 2 ticks here is 360 degrees. It's a full period of that clock, all right? So I set it high, I wait 1 period, which is what this specification is for. Then I set it to 0. Then I wait a little while. Then I set it 1 for 1, period, wait a little while, and so on. So what I'm doing here is I want to just see if it works. And we'll fire up the waveform viewer, and we can see if 1 period on this clock is recognized and outputted for 1 period of clock 2. All right, and it just does it a couple of ticks, and with different delays, we'll see some of it works, some of it doesn't, and how if we violate PLOT, if we violate our requirements, our assumptions, what's going to happen in here. Okay, so this one's running slightly slower. And what we're going to find, I'm pretty sure, is if clock 2 runs slower than clock 1. I mean, think about that, right? You could have a situation where clock domain 1 could do things too fast for clock domain 2 to ingest the things. All right, so I think that's what I've done. I've created like an example in here or two where it won't work, and then we'll look at why, and then we'll see what happens when clock 2 is running faster than clock 1. So here are the two clocks right next to each other. We can clearly see clock 1's running faster than clock 2. Let's put clock 2 back down here near our output. Here's the in wide. That's the output of the clock 1 input. We can put that right next to in. You can see it's actually just doubling the length of the input signal here. Let me turn on my horizontal bar thing. This is our counter in here, and this is the next, and this is the register, or the current value, I should say. What's out down here is the output. So you can see here's an input right there, and there's the associated output, and it takes a little while because it's going through shift registers and pulse stretchers and all this other things. So this should give you some understanding of the pros and cons of using synchronizers of different kinds of designs. It obviously delays the knowledge of this input signal here by some period of time before it comes out down here. But look what's happening. This input signal is coming from this input clock domain. Now, if we zoom really far in, I purposely put a slight delay in here in my test bench. And the reason I've done that is because if you're using a bunch of these blocking assignments and you're doing this in simulation, you can end up with the simulator doing things in kind of random order. And what we know is by the specification of what I'm talking about here, this being the rising edge of our input signal, this input is risen in this clock domain as a result of this rising edge here. It's 100% certain to go high after this signal does. So I made it a slight delay in here so the simulator can't fool us if they all go high at the same time and the simulator does something in a weird order. That's why this is delayed. This is very realistic, okay? That's what's going to happen. So every signal in the clock 1 domain here, actually the entire simulation, is skewed slightly off of this so that the simulation doesn't screw up. All right? What do we got here? This should also go down. It doesn't. Ooh, I'm lying. Oh, that's not the right signal. This is. Yeesh. Okay. So it also goes down as a result of the next rising edge. So in other words, the relationship of this input signal here that's created in this clock domain up there is realistic. Okay, that's all I'm saying. This other stuff that's going in the state machine up here is actually happening in sync with the rising and falling edges, which is very common in your test benches and things. And that's not necessarily wrong because these are assigned using non-blocking assignments, and the simulation is more accurate and correct in that case. Okay, just so we realize what's happening there. If you have zoom in and have questions and you're looking at the stuff later on, that's why I did that. Okay, so what do we got here? In goes high for one period and then goes off. The stretcher kicks in because when this is high on a leading edge of this clock here, that's when my counter advances here. It knows it's going to advance right away because the next is set to true because in is high in the combinational circuit in the code we just looked at. So on this rising edge, it's transferred to the register, okay, from the combinational circuit output, and that's when it goes high here, it becomes a 1. So this down here, the output wide is true the whole time for 2 periods long. And it's long enough that at least in this case exactly one rising edge of the clock 2 free running clock 2 signal sees it high here, and it's going to start shifting it into which shift register we just see it do right there. It's triple zeros. It shifts that thing in on the most significant bit right there. And so it's now captured and it's going through the regular, a metastability synchronization logic. And on the second time the clock 2 rising edge goes by, we have our 1 0 in our shift register, which is used in that AND circuit to generate this output right here, which goes true as long as there's a 1 and a 0 in here. Turns out there's a 0, 1, 0, but it doesn't matter. We're only looking at these 2 bits on the right. And that's our output signal right there. The thing works fine. Okay, so let's see what happens if you do it again, like pretty darn soon. Look how quickly this thing goes active again. All right, so it goes active again right here. That's a bit of a problem. It could be a bit of a problem, but it's good enough because we already saw this signal here. We can start shifting bits in again right away. As long as there's 1 0 bit in here so that we end up with a 1 followed by a 0 again eventually, we won't miss this one. This is about as soon double fire in a row as you can do this. Okay? And this is really soon because this clock here is running a little slower than clock 1. All right? So if this guy does it too often, we're going to miss it. You're going to see that at the end of this waveform. I did that on purpose. Okay, so here's the second one. It's going to work again. It starts shifting it in right here. You got your 1, 0. There's your output there. So it's working along just fine and dandy. Here's another one that's pretty darn soon. This one's got a, right away. It starts shifting another 1 in right away. But you can see that this one works again and for the same reason. Okay. Then we wait a long time. The thing clears out all the way to zeros. And it starts again at the beginning. And of course it works. This one, what are we at here? We just barely missed it here. This is a great example of what happens when, your target clock domain is rising at the same time as its input that it's trying to sample. In this case, what does it do? It actually sees it as a 1 here. It could have just as easily seen it as a 0, but it saw it as a 1. That's fine. It sees it as a 1 again right here, so that you can know that because there's 2 1s already shifted in here. And there's your 1, 0, which generates the output. And now it's got a 1, 1, so it goes back off, right? And now it's shifting its way out. Here's another input signal. So this is happening super, super soon. It's not even clearing out all the 1 bits, and it's starting to shift in another one already. That's actually okay, because as long as there's 1, 0 sitting in here, it'll eventually have a 1 followed by that 0, and we've got our output. Again, we zoom out here, we're looking pretty good. Here's an input, output, right? Here's another pair, input, output. Here's another pair, input, output. So it's working over and over with little bit differences in the delays in here, but look what happens down here. I purposely put a whole bunch of these in a row. Is if you look pretty closely in here, see how this is a little bit later than it was over here? This one, they lined up just like right at the same time. This time, this clock edge here is ever so slightly after this input there, okay? This is another example where this leading edge is inside this thing and we shift in this 1. Down here, it's going to be a little bit later because they're different frequencies. And what do we got here? Here's one where it's like all the way over here, right? And here's another one that's a little bit later still, and one that's even a little bit earlier, okay? And then it finally sees that it's high on this edge, all right? So we're going along. Here's one where it sees it here, and we got an output, and now we've got one right there where we're in trouble. There's a 1 on the left here, and we got a rising edge, and it sees it high, so it shifts in another 1 here. This is an example where this one here, this input pulse and this input pulse are just too close together. Just ever so slightly too close together. Because what we're seeing here is that clock domain 2, when it's sampling, it never saw it go away. It never saw it it didn't go away long enough, okay? What happens is, this one goes, that one goes, but this is stretched. And this gap here, look what's going on in there. There's no rising edge between here and here. This rising edge in this simulation happened either coincidentally or ever so slightly after that rising edge, and it never saw a 0 in here. So this is your problem when you're tuning these things. So this is an example of it not working, is what we've got. When clock 2 is running slower than clock 1, you cannot generate input pulses too close together in this case, whatever these are, they're ever so slightly too close together. If you just had one extra clock cycle of delay in this clock 1 domain up here, this would have been further, these two input signals here, this is your input, right? These two signals here would have been stretched out or moved apart further than they are in here, and it would have given it enough time for this gap in here to be big enough for the clock 2 sampling to notice that it went 0 and back 1 again, all right? So that is your downside here. You need to know how to tune these things. You need to know what the rules are going to be in clock domain 1. So one of the rules we already know. In order to use the circuit I've got here, we need to have the input signal needs to be 1 period long and already synchronized in the clock 1 domain. And then we can stretch it out. Then we need to make sure that in clock domain 1, the input signal, actually, which is these bumps here, which look a lot like those up there. I got confused for a second. As long as these don't happen too often, we're fine. So the rule is probably we need one more clock than we have here, right? So what do we got? We have 1, 2, 3 periods between this one and that one there. This circuit, when clock 2 is running at the frequency it's at, and clock 1 is running at, relative to each other, these two frequencies, this rate that you generate these inputs cannot happen more often than once every 4 clock cycles in the clock 1 domain. Because this is 3, it's too often, it missed. Okay? There's a failure. So let's get out of here and look at the other one. And let's also talk about a potential flaw in this design before we hang up the old phone today. Okay, no, I'm not going to change the code in here. We're going to go to the test bench, and we're going to change the frequency, and we're going to sample it a little bit faster. This one here is closer to what I designed it for. I designed it to do this, where clock 2 is running so slightly faster than clock 1, okay? But not super fast, right? If clock 2 is going, 1.5 to 10 times faster, anything more than 1.5 times faster than clock 1, I wouldn't use this at all. I would just use the other synchronizer that you already saw, and that would be fine and dandy. But it's not going significantly faster. So we have to worry about this idea of stretching out the input pulse in the source clock domain. Here's all the signals. Let us zoom out and look what we got here. Now, we got the same thing we saw before, but look at over here. Now you do see the 2 pulses over here in the far end. Last time you saw all these pulses, and then you saw the pulse there, and you did not see this one there. So this one's actually working pretty darn good. So when we're going to a faster clock, well, let's put the clocks next to each other and get a good eyeball on that thing. We know, because we set it, this one has a smaller delay between each tick than the one above. So we know it's going faster, but you can clearly see that here, right? So let's organize these up like we did before. The output, you can just get the reset out of the way. And there's the FIFO, because this is kind of the same order we had last time. So what happens here? Again, the same thing with the ever so slight delay. So the simulation is right. What do we got? We sample the input on the leading edge here in clock domain 2. We're looking at the stretched out signal, and we see a high. We shift it in. And the next time we shift it, there's a 1 followed by a 0. So the output goes high for 1 period of the clock 2 domain. And we actually see another sample on the stretched out signal up here. That's our 3rd time, so we see 3 1s in there for all already. So this is working great. Now we know it's not going to get fooled this time. And although it could still have 2 of these super close together, and we would miss it, right? I mean, if this thing went high again right away, it probably wouldn't work. Yes, it would not, actually. So we need to be careful of that. We have to wait until the stretched out signal goes low for 1.5 periods of clock 2. I mean, that's the way you would do this. You would say, I need the frequency that the input can change has to be less often than 2 periods in clock 1 plus another 1.5 periods in clock 2, which is just the extension of make sure you sample it at least 1.5 times faster than it's being created. And in this scenario, that's what the math would map to that number of clock ticks in these two domains. All right, so this is looking pretty good. Clock 2 is ticking along pretty quick, and in the test case, there's plenty of edges down here for it to see that it went to 0, and now it's going back to 1. And again, you can see it floating through, and you can show, you can zoom in on this to your heart's content. I did enough of these because this will slowly wander in phase relationship to the input signals, is why there's so many in this test case. So here's one right after it goes high, you see the input changing. This one after it goes low, the input changes, and so on. So you'll see a little jitter on the output relative to the input. There's always this little bit of a delay in here. So many clock pulses later, you will ultimately see the output go high. The worst case scenario is that the input signal, when it goes high, won't be seen for as long as a whole period of clock 2, because if it goes high right as this is going high and it didn't see it, you have to wait until the whole next period comes along. So that's one whole clock period before you even see it the first time, and you have to see it twice for it to shift through this register in order to get the output pulse to go there. So the delay would be 2 whole periods of clock 2 before the leading edge of this output signal. And normally this would be used to enable something that would then clock in and react to it on the next leading edge over here. So this thing really would react within 1, 2, 3 periods of clock 2. That's how long it would take before you can react to this output down here. Okay? And this delay will become important if you ever use this. You know, how fast do you need to be able to respond to something changing on an input? You know, when you use a clock synchronizer, you don't have a lot of luxury. You have to deal with some form of a delay of some kind. Or you have to get really creative and come up with a whole nother way to solve the problem, which you're free to do. This one seems to work for me, at least in this simulation, okay? Now let's talk about the simulation a little bit before we hang up for the day here. There might actually be a problem in this design that I have not yet found, and that is this. I'm playing some games here. I take the input wide and I set it 1 here. And this input wide is being clocked in down here. This is not synchronized. Well, it is. Input wide is synchronized in the clock 1 domain. However, it is not a register that gets loaded by the clock 1 active going edge. I don't do that because I wanted it to go high as early as possible. I didn't want to wait a whole extra clock 1 period before the in wide reacted. So I actually set it true in the combinational circuit down here. I set it true when in goes true. And I'm kind of a lazy oaf, and I justify that by saying, well, I know, because the requirements to use this design, I know that in is already supposed to be synchronized in the clock 1 domain. So in a way, this should be safe. However, it might not be safe. It could glitch. It could glitch. And it could glitch because what happens is that, remember, in is going to go false in reaction to the rising edge on clock 1, where the period, the tenure of this signal ends. It will go 0 in reaction to, as a result of clock 1 having a positive edge on it. And at the same time, my counter register will be loaded with counter next, which is set to count reg +1, which then this will become true. So this becomes false, and this becomes true at the same time, which means this combinational circuit could actually have a little bit of a glitch and then go true again for like 1 nanosecond or however long the propagation delay is through the latch that does this when this circuit is being, used to evaluate this expression. Because this one will change and that one will change very close to the same time. Nothing's perfect. This could actually glitch ever so slightly. There could be a flaw in this design. I'm warning you, if you use it as is, don't come back crying at me. This probably is fine, but I don't know it's perfect. Therefore, it's probably going to fail in some catastrophic way. And we'll find out more about that when I try to apply it in a real circuit. In other words, I may have to do something in here to prevent it from glitching during that period of time. So we'll look at that more closely when we put it on a scope, when we try and actually hook it up, generate some signals from real circuit and stuff like that. All right. So this might not be super safe. I'll put a warning over here. This is dubious. Okay. This may be dubious. I'll go as far as to say it is dubious, all right? So flame away and tell me how to properly do this. It's not immediately obvious as I sit here talking about it, because I just wrote this up recently, and I haven't really had a chance to test it on a real circuit. But like I said, this is not something that's a great idea to do, okay? What I could do maybe is change this to the negative edge on clock 1. That might solve the problem flat out, because then this transaction will, that is the solution. But now that I think about it, here, I'll show you what that's going to do. Because in is supposed to become true on the positive going edge of clock 1, if I then use the negative going edge in this logic here, what'll happen is that this transaction will occur 90 degrees out of phase. The input signal here will remain true for half the period of clock 1 after this already is counted to 1. Okay? This would solve this problem. However, it may create a whole new one. By doing this, what'll happen is this won't glitch in here, but the total period of time that in white is true will now be 1/2 a clock period less than it was when I clocked it on a positive going edge. So let's go ahead and do this. So these are all the things you need to think about when you're tinkering around with your circuit. If I want my output to go true fast as possible, there are going to be some downsides, and it depends on how you deal with your circuit and what's okay and what's not okay. And as you look at this here, it's working perfectly. However, it may not. If you look really closely, see, this is now doing this wonky thing here. Is that the input signal? Yes, okay. And that's actually okay. The input should be 1p. Oh, let's organize these so we can see them. No, I'm in overtime. I didn't really mean to fix this. I want to leave it as a task for the viewer, for fun. Now I'm ruining all the fun, But that's what I do, Us YouTubers are doing that sort of thing. So, okay. So here it is, our slightly delayed. This is broken. That's clock next. Here's in. Okay, fine. Get these where I can read them. Okay, there we go. He goes high as a result of this rising edge in the clock domain that feeds this circuit, okay? Then, since he's high, what happens? The counter goes on, in wide goes high along with this one, and he's going to go high for 1.5 now periods instead of 2 periods. Okay, so you need to make sure, and this is, again, back to your timing. It's okay to do this, but I just shortened the period of this signal here. And I now have to ask, is it still going to be long enough to meet the criteria? One way of saying the 1.5 periods in the receiving clock domain is 3 edges. 3-edge rule. 1 edge, up, down, up. Is this signal always going to be long enough such that 3 edges of the clock domain that it's driving into will always pass while this signal is true? And the answer is clearly yes, okay? Given the relative frequency difference we have here. Again, back to the design, back to this particular specific application, and for me playing games and propagating the input signal to the output using a combinational circuit, and then doing it. And here you can see, this is probably the counter right there. There's my counter red. This is exactly the transition when in goes false and the count advances down there. That's not in, this is the counter next, for crying out loud. In goes false now over here, a half a period after the in, or the counter. My God, I can't even talk. Bear with me, folks. I'm not going to edit this out. I'm going to just move on. This down here, now, because it goes high on the falling edge, you know, the sequential circuit that recognizes the input and advances the counter on the input side that is synchronized in the clock 1 domain happens earlier than it did before. And the next signal always would go true right away, along with the presence of the input signal, which we saw last time. And of course, it will go false as soon as the counter advances, because that's what it's going to do. It's a combinational circuit, and it reacts to the fact that this thing just ticked forward. Okay, now, this is high for at least 3 edges, could even be 4. 1, 2, 3, 4. Exactly. Maybe even 5. If they slid over to there, we might even pick up another edge. So this time, relationship is great, provided that the clock 2 doesn't slow down too much. And we can slow it back down, and we'll probably see it fail. All right? So this will probably take care of the glitch problem. Let's put that glitch problem back in case you didn't see it, because I did all this in my head and I was clowning around. Put this back to positive edge. Now the comment is true. We're back to being dubious. So what did we see last time that I probably should have pointed out while we had it up here in the first place? Come on, open this up here. I got to remember to do this on the scope. It would be nice for me to tweak it and slow it down and speed it up to the point where we can actually see the slight glitch, because it will be there. And it could fail because this is, the sort of setup and hold time thing that's going to cause you a problem. So there's the register and the next, and these are going to do that. The key was that this edge here and this, which were the 2 edges that were screwed up. When the input signal goes away, yeah, these are the one. Where the heck is the input? Come on. Put the input up here. Thank you very much. When the input signal goes away and the signal over here goes high, that's the problem. And I skewed the input back ever so slightly. I probably should have made it go low over here for this illustration. This will go low and this will go high. If it does it like like the simulation is right now, we're fine because they're both high at the same time. But if this goes low and that one goes high at the exact same time, or ever so slightly early, which could easily happen, right? Because everything doesn't happen in the same propagation delay as a result of this rising edge here. These could be all over the place, related to each other. If there's a gap between them that's not like this, then this down here could see a slight, it could miss the, it could definitely miss the signal. It could see that little 0 in there on the clock 2 rising edge here, which is this signal here, and I'm moving them all over the place to confuse you on purpose. Get this up here. This is the order they were in before. So if this rising edge that is sampling everything, because it happens to be so close in this particular example, it's a very amazing coincidence that it just happens to sample right here. If this one hesitated ever so slightly longer, it would see that gap, is my point. Now, by changing the circuit that advances this counter register here on the falling edge instead of this rising edge, what happens is that the counter that we just saw in the previous diagram would have gone high over here and guaranteed that it'd be high at least a half a clock cycle before the input signal goes away. So let's put that back up. I'm jumping all around. This is actually probably a pretty good video to show you all this, because you make mistakes like this all the time and you want to be able to recognize them. if I fixed this and then filmed it and never even mentioned that this could be some dubious thing for you to watch out for, which is no longer dubious, then you might not have even thought about it. And honestly, debugging one of these is an incredibly difficult thing to do when you got it in your head that you're right, and I still might not be right. No one's ever really right about synchronizers. This is all probability and statistics, because circuits hesitate and they don't. And you know, when you have a metastable situation occurs, it could take, in theory, an arbitrarily long time to settle out. And what we're doing is I'm making the argument that the amount of time that this thing would require to settle out is not very long relative to clock 1 and clock 2, and that the gates, the flip-flops, will stabilize well before, you know, the next time one of these edges arrives. So here's the situation where we have this fix to the glitch, where in is known to be active for a full period of clock 1, which is up here. In goes high here, and then it goes low on the next leading edge. And because the counter is now advancing on the falling edges here, this overlap where they're both true is guaranteed to be clean and keep this wide input true for not 2 periods, but at least 1.5 periods of clock 1. So do all your math based on 1.5 periods of clock 1. Has to be, less than 1.5 times the frequency down here. Because that's going to be how long this signal is. And this signal is clearly like 2 to 1. We got plenty of edges down here. This will work fine, okay? And it does in this particular example, all right? So this is probably, actually, I could have organized it a little better. I'm sorry. It's probably a pretty good example, though, of a walkthrough of one way to solve a problem that you can still do using an open loop circuit. This is called open loop because the clock 2 domain is not like receiving it, acknowledging it, and then sending back to clock 1. Okay, I saw it. You can send me another one with a full handshake kind of thing going on. And the reason I'm doing this is because I want to hook an FPGA up to a Z8S180 that's an asynchronous chip, and it does not have handshaking type logic. So I have to react, and the amount of time it gives me to react, and I need to be able to do it in one clock domain while the CPU is running in a different clock domain. So I decided to use this technique, which is going to work provided that the frequency, how often I get an input signal from the CPU, is never too close together to screw up the logic in my clock 2 domain. Now, my clock 2 domain in my circuit that I'm working on is faster than the CPU domain. So it most likely will be fine, provided that I never assert my input more than once every couple of cycles in the domain that comes, that is clocking my CPU. And it turns out that I want to hook this up to a memory port or an I/O port off the CPU, and on a Z80, the absolute most often that it could ever theoretically access 2 memory locations in a row is actually 3 clock cycles in a row. So that might not work if I hook this up for memory. Actually, it probably will. It looks like it would here. I'd have to do the math to find out. And I'll do all that when I hook it up for realsies. But what I'm going to hook it up for in my first implementation is 2 I/O port addresses. And when a Z80 accesses an I/O port, the CPU can never do it more often than once every 7 CPU clock cycles, which would be my clock 1. And this is going to work fine with 4. It might even work with 3. I'd have to do the math. And I also know that my clock 2 in my application is actually running, I think I actually worked the math out on this one to make this be representative of those 2 frequencies, and this is an actual relationship that's accurate. So I don't know what would happen if I moved it way over here. This video is getting too long. I'll leave that as a test to the viewer. I can see if I move it over there, what would happen then is my in wide would go back high here, and we would fail the 3 edge rule, it won't work with 3. It will work with 4, but it's not going to work with 3. So this is actually fine for I/O addresses on a Z8S180, which is the CPU I'm using, because the CPU can never do it more than, like I said, it takes it at least 7 of these clock cycles up here between 2 I/O accesses. So this is fine. If I ran a DMA controller, it would also do it once every, how often would that work? It still would have to do it at least once every 7 clock cycles. So again, I'm okay. This is going to be good for my purposes, provided that all my math and stuff is right. Even with the 1.5 clocks and me advancing this counter on the falling edge of this clock up here. So the only other thing I haven't really talked about, I mean, I was kind of cavalier about changing this from the positive edge over here and reacting over there to over here, so that when the input signal is going low, I don't go low here and high with my count at the same point, okay? That's what I did to fix that. However, you know, can you really be this cavalier about these things? And the answer depends on, did you now violate your setup and hold times? Well, it turns out that this thing here is running on the order of 20 megahertz. And that here is the period of a 40 megahertz clock, okay? So 20 megahertz is what, 50 nanoseconds or something like that? I think that the setup and hold time for the flip-flops and stuff inside the FPGA that I'm using, even the worst FPGA out there, is going to have, you know, a couple of nanoseconds would be an infinite amount of time. It would be a really bad FPGA to need a couple of nanos of setup time. So this has got more, let me just say, it's more than 10. We're way in the safe domain. It's probably 1 or 2 nanos for the setup and hold time for the gates inside the FPGA. So for me to take this and move it from here, this edge used to be here. Now I moved it over there. I give it only half the time. I cut the setup time in half. Is that safe? I'm going to say yes, because the frequency of this clock is not very high. The whole thing is not running very high. All these frequencies in my system, this is about 20 megahertz. This is going to be about 25 megahertz. So these setup and hold times well within the realm of reason. Even being cavalier and cutting it in half, it's still going to be long enough in my application. Which brings us back once again to the README file. Keep in mind that you have to, it's pretty much always necessary to tune any synchronizer that you steal off the internet or even come up with your own. You have to tune it to your application, all right? So I wrote one that was sketchy and I fixed it. I think this is going to be great for what I want to do. This rule of thumb here, I stole from another guy who stole it from another guy who stole it from another guy, and so on. All right, so this is a common rule of thumb. You can't go wrong if you do it this way. And that's where we're at least with the numbers that I want to use. I'm going to commit this to share what I got here. What did I do? I changed, I changed the test. Why did I change the test bench? Change the test bench here to change the clock speed. And I changed the edge in this file from positive to negative. What else did I do? I also fixed some dock while I was in the neighborhood. All right. So let me go ahead and add this, commit it, push it out. Thanks for watching. Let me know what you think. Let me know if there's a better way, because I'd love a better way. But this is probably good enough for my needs. So thanks for watching. I'll see you on the internet.